Hey everyone, so we are on video number 4 and we'll look at some additional alternative resources to the traditional ones and looking at also how we can potentially consume a bit less. So this video should be a bit short. I will just go directly towards it by presenting you those two options, cogeneration and landfill biogas. Cogeneration is the idea that when you producing something, you're making something, you're always losing heat in the process. So for example, you're producing electricity from a digester. So that would be in fact using some bacteria to decompose some kind of product. This will, before you get all your product creating your electricity, this will engender some heat that will be lost. And so with cogeneration system, you're in fact trapping this heat by, for example, running a liquid just above it. This liquid will be warmed up and you're able to use that as to produce, for example, a secondary type of energy, maybe to warm up your place or to cool down your place. So cogeneration is the idea that you're producing either electricity or heat, you're using that energy that normally should be lost in the process. So you're making sure that you have your main production line right here, and you're creating a second production line there by using the product that is being wasted. So cogeneration really look at the waste happening during your production and trying to make sense of that waste to use it to produce another source of electricity or another source of energy. Then, and what we can also do is using our landfills. Our landfills are places where we throw our trash. It's made up of a lot of stuff, but it's including a lot of organic matter. A lot of food are being thrown over there. That food will be decomposed. Mostly it will decompose, cut down by the oxygen because well, we accumulated and accumulated and accumulated waste over it. So a lot of bacteria will decompose that organic matter and that will form some methane. This methane is a natural gas that is in fact burning not naturally, and normally if it's just released in the environment, it's participating to global warming. However, we want to use this methane, we capture that methane and we're able to burn it down to produce electricity. So we can use the landfill to do that. The food waste being thrown in the landfill will in fact being a source of decomposition. The same also we can use sewage treatment power plants. The sewage coming from treatment plants or the residual coming from animal feedlots can be used to decompose, create some methane, and from that we just produce electricity. And I have this little video to show you.
Here in New York City's Fresh Kills landfill, officials are making sure not to let the city's trash go to waste.
Beneath my feet is the household waste and the municipal waste. The garbage is decaying, generating landfill gas.
New York City is capturing the methane gas created by decomposing trash at Fresh Kills, processing it, and turning it into clean natural gas.
We're probably the only facility in the country that the gas from this goes right into someone's house because of the safety measures and the gas quality.
The 2,200-acre landfill, which was first opened in 1948, is no longer accepting garbage. The city is in the process of turning it into a park. But the decomposing waste that was dumped here decades ago continues to generate methane.
It could be food waste, it could be paper waste, it could be rags. We're talking about solid waste that the general public used to dump years ago.
Fresh Kills is one of 30 landfills around the country that have projects to turn landfill gas into high BTU pipeline quality natural gas, according to the Environmental Protection Agency, enough to heat 342,000 homes each year.
I'm here at the Fresh Kills landfill, and I have to say, I would never know this was a landfill. You look behind me, you see all this vegetation on this hill. This used to be all marshland. It was all flat. Below my feet, up on that hill, that's all filled with waste.
The conversion process at Fresh Kills works like this. The landfill gas is extracted using high vacuum pressure through wells and blowers and then cooled. It is then piped to a purification facility where the methane is isolated, scrubbed, and cleaned. Because methane is odorless and colorless, it is then mixed with a chemical deodorant called mercaptan so it can be detected. From there, the resulting natural gas is piped directly to about 22,000 households on Staten Island. The city has paid $12 million each year for the gas, which was once simply released into the atmosphere. Now, thanks to state-of-the-art technology, a landfill that was once a symbol of environmental neglect is a place where trash becomes power. Brian Montopoli, CBSNews.com.
So in this case, in fact, as you could hear, the methane being captured by the factory or the plant, sorry, was not turned into electricity. So they didn't burn it out to make some steam and burn and to produce electricity. But in fact, they use it and clean it just to be used as natural gas to be sent to residential, where it can be burned out in the stove, for example, or in the water tanks. So this is another way, another source of natural gas. Then, as I mentioned, we can use also animal feedlots, the residual from animal feedlots to produce electricity or to produce energy, and that will be the topic of the next video.
More than 70 million gallons of milk are produced in the US every single day. And when you look at the carbon footprint per each gallon of milk, the cow produces about 2 gallons of manure. The manure has a lot of carbon.
We have to be smarter about the way we recover those nutrients and deal with those wastes for their energy content and nutrients in a more sustainable manner.
Hydrothermal processing is similar to cooking in a pressure cooker. We combine waste from different sources such as dairy manure, food waste, sludge from wastewater treatment plant, and we mix that waste with high temperature water under high pressure. In these conditions, the organic matter in the waste break down and reform to produce biocrude oil, which is similar to crude oil, and after refinery process can be used as a transportation fuel. Food waste to energy is not a new thing, but our approach enables the processing to be much shorter in terms of few minutes compared to few days or few weeks. The motivation is beyond climate change. It's a sustainability question. It's our footprint in this planet.
We should be always striving to make systems work better. And if the energy footprint becomes one of the metrics that we're sort of judging performance by, I think you will be moving in the right direction. These small changes sometimes might seem so incremental that they don't matter, but they do matter.
Treating waste as a resource is an important piece of the sustainable future.
Right? So we have other way, other fuel, and other, in some way, technology also to use our energy. Transportation, as I mentioned, mostly rely a lot on fossil fuel. We use in most of our cars use gas, but with new technologies happening now, we can see the emergence of more and more hybrid vehicles and, in fact, more and more electric vehicles. And so those are better because it's relying less and less on fossil fuel. However, that depends if what you use to produce electricity. Majorly in the east side of the US, most of the electricity is still generated by coal. And so if your electricity is generated by coal and you have an electric car, you're still kind of indirectly producing, you're still using a bad energy for your transportation. So this, of course, has to change. Another issue, and that was the issue of the past, and that's becoming less and less of an issue, is the storage regarding electric vehicles, because the battery were really big. But thanks to our technology advancing, we are in fact able to do better little by little. Another source that was used over the last 20 years, more or less, kind of a down now, is biofuels, where in fact we're using ethanol coming from mostly crops of corn in the US, and they're using palm oil in Europe, for example. They use this mix to reduce the amount of fossil fuel being burned in the car. So mostly that allows to rely a bit less on fossil fuel, but it's still participating in greenhouse gases emission. It's participating in deforestation, possibly, because it's coming from an agricultural resource. It's participating to eutrophication, water pollution, soil pollution, and it's competing in terms of the corn, for example, Brazil is one of the big exporters of corn for that reason. And instead of using that corn for their population, it's sending it away to other countries. So there is a big issue about nourishing, feeding their population, and also on the price of those of that corn. Then a technology that has been under the work for a while has been the idea of the hydrogen fuel cell, where we're mixing two elements that we found everywhere on the planet, hydrogen and oxygen. Those are atoms in huge abundance in our atmosphere, and we are making them react to produce water. So ideally, this reaction will produce electricity, or it will produce energy, electrical energy, without producing any greenhouse gases, just releasing water. So it will be a clean and green energy to use. The problem is, first you have to break down most of the time hydrogen and oxygen, and that requires electricity, and that can come from fossil fuel. At this point, it doesn't have a good yield in terms of energy, only 35% of that reaction producing energy. So it's not very good still. And then the also big issues is the volume. It takes a lot of space, a lot of storage. And so the hydrogen fuel, has some potential in the future, but for now, everything seems to be, for transportation, to be turning mostly into hybrid and electricity. Then quickly, we also, as in terms of our consumption, should make some improvement, and more we're moving from what we call a traditional type of electrical grid to a smart grid. What is a traditional grid is the idea that, well, you have the generator producing electricity and sending the electricity, everything is connected, and we're sending the electricity everywhere. Whatever, if you need it or if you don't need it, it just goes. The smart grid, the idea is, first, instead of relying on fossil fuel energy, you're relying mostly on renewable energy. You're not connecting everything to the same power plant, but in fact, you have some satellites in some interconnection, and you have some monitoring happening to send electricity to the place that needs to be used. You have what we call the two-way meters to make sure that there is demand, and so we can send electricity there. There is some smart control happening with some storage also that allows for electricity to be sent away at further distance. And that allows for electricity to be better distributed, meaning that we are wasting less, we are making more use of what we're producing, and we're producing, in fact, what we exactly need. So this has helped to reduce our consumption, or at least to make our production fitting our consumption. Final thing is, with all the advancement, unfortunately, we cannot escape what we call the rebound effect, part of the Jevons paradox. The idea is, with the rebound effect, mostly the Jevons paradox, is we're making this improvement in technology that will, for example, reduce the impact on the environment. But because it is an improvement, more and more people will use it. And indirectly, by using more and more, the impact on the environment stays the same, or in fact is bigger. See this figure right here. It says that fuel efficiency tends to have increased and not decreased fuel use. The reason why is because with fuel efficiency, people are traveling more. They think, okay, my car, with the same amount of gallons, I can do 400 miles instead of 200 miles. So let's go for more vacation. And at the end, it's increasing the fuel use, it's increasing the impact on the environment. And this is what we call the Jevons paradox. And I will ending up this video with these short movies.
Energy efficiency is a good thing. The smarter our cars, the less greenhouse gases we emit. The more intelligent our light bulbs, the less electricity we use. But what if this isn't necessarily true? Since the oil crisis in the 1970s, cars have become more fuel efficient. But we're still using the same amount of petrol. Why? Because people are driving their cars more, and they've grown larger and more powerful. We're also using more electricity in our homes, despite energy-saving technologies like LEDs. It's because we're offsetting any efficiency gains by buying more appliances and larger houses. In 1865, an economist called William Stanley Jevons discovered an inconvenient paradox about energy efficiency. While England was racing to make more fuel-efficient steam engines for its industrial revolution, Jevons predicted a surprise. Rather than using less coal, he said, society would consume more overall, as better engines were adopted for more purposes. And he was right. More efficient engines generate more opportunities for new uses and the chance to profit, driving up demand and economic growth. And we're seeing the same thing today. Fridges are more efficient, but we've cancelled out any efficiency gains by making them bigger and buying more of them. This graph shows the paradox in the aviation industry. While planes are less fuel intensive than 3 decades ago, we're flying more than ever before. And despite the fact that the US has cut its energy intensity by half, overall energy consumption has risen by over a quarter. Now, Jevons's original ideas are being revisited. Sometimes economists call the paradox rebound effect, but there's a key difference between the two terms. While the rebound effect measures a loss in efficiency gains, the Jevons paradox points to a deeper problem. That more efficiency alters the economies in ways that can't be measured, because the effects are too complex to be captured in economic models. Take the knock-on effects of efficient light bulbs. They can lower electricity bills for companies, reducing the costs of goods and services. But lower prices may then boost demand for these products, which increases energy use overall again. This isn't to say that energy-efficient technologies shouldn't be promoted and utilised. But without a better understanding of how complex systems adapt to changes in energy efficiency, we could end up using more resources than we bargained for. And to avoid the Jevons paradox, we need a more reflexive and responsible approach to governance.
All right, and we are reaching the end of this lecture and the end of this video. At this point, I just have a couple of questions for you that you should be able to answer. I think those questions will be asked in discussion, so you just think about it. They concern mostly the first, the part of the video about non-renewable energy, so the video number 2, and also number 1. There will be more questions to come during discussion. But for example, you might think about limitation of each energy resource, the main use of coal, petroleum, and natural gas. We saw that. Why are we always, when we convert some source of energy into electricity, we always end up with less electricity, less energy that we had initially? Why is that? Why are we considered fossil fuel non-renewable? So I let you with those questions and be ready to answer them during discussion. And with that, I'll see you for our next lecture, which should be on freshwater. See you later.